Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will begin to discuss Ohm's law. Alright, so many of you, if not all of you, have almost certainly seen what is known as Ohm's law before. Ohm's law is a sort of classic rule of introductory circuits. It's almost always taught if you've seen circuits in any class at all, so in an 8th grade physical science class, for example, that sort of thing. So the question is, if the resistance is defined to be delta V over I, isn't V equals IR always true? So this V means delta V, it means the potential difference, and this is the classical representation of Ohm's law. So just like some people have F equals MA memorized, and it's sort of a famous equation, this is the equivalent, which is known as Ohm's law. And so the question is, if this is a definition, isn't this always true? And the answer is yes. It is always true. The resistance is always defined to be delta V over I, or the potential difference divided by the current. But the resistance itself of a material is not always constant. It's not always exactly the same for all circumstances, for all values of I, and for all values of delta V. And so what Ohm's law actually is the statement that if a material obeys Ohm's law, that the resistance of the material is constant at all temperatures. And sometimes what we mean by that is mostly constant, or pretty close to constant. So the classical representation of Ohm's law as V equals IR is okay. It just implies that the resistance itself is constant. So the problem is, in general, the equation delta V equals IR is always true. But it's not always true that R is the same value for all temperatures, currents, and potential differences. And so what Ohm's law is actually just a statement that the resistance is constant. If the material obeys Ohm's law, then the resistance is constant for that material. We call materials that obey Ohm's law ohmic conductors, and materials that don't obey Ohm's law are known as non-ohmic. An example material that is almost always ohmic is a metal wire at low temperature, or lowish temperature. Sort of, because it's important that it's constant at all temperatures, we're sort of talking about a range of temperatures. Obviously, if the temperature gets high enough, the metal wire melts, and in that case, it definitely doesn't obey Ohm's law. But for all practical purposes, the resistance is constant for a metal wire at normal values of potential difference, current, and temperature. And in that case, it's an ohmic conductor. So strictly speaking, very few materials actually 1000% obey Ohm's law, or obey it for a huge range of values. But many materials sort of obey Ohm's law, and so that's why it's kind of famous. Another way of stating this is that the Ohm's law is a statement that for that material, the ratio of the potential difference to the current is constant for all values of I and delta V. And as I and delta V increase, often you find temperature increasing. So an ohmic conductor will have a straight line between delta V and I. Notice that the value of delta V divided by I is R, and that's constant, which means that that ratio will be the same for an ohmic conductor. All right. So let's take a look at a number of graphs for ohmic conductors that sort of illustrate the differences between what's going on. The first is that delta V versus I graph. So if the potential difference is graphed on the vertical axis versus the current on the horizontal axis, then the value of any of these points, delta V divided by delta V divided by I, will be equal to the resistance. all right? And that is equivalent for an ohmic conductor. We got to be a little bit careful. That's saying sort of that ratio corresponding to the value of the slope at the point is equal to R. It's important to recognize that delta V divided by I is not delta V divided by delta I. So it's not actually the current, the gradient, but it does correspond to the gradient for ohmic conductors. Notice that you can also plot I versus delta V, and actually this is often preferred, mostly because delta V is almost always the independent variable. You're almost always adjusting the potential difference across a circuit element directly, and that interacts with the resistance in the material to produce the current. And if you graph I versus delta V, I on the vertical axis, potential difference on the horizontal axis, then the value of the resistance can also be found by taking the value of the slope or the value of I divided by delta V at any point, and that gives you 1 divided by the resistance rather than the resistance itself. Notice that you can read off either of these graphs whether the resistance is higher. So for a delta V versus I graph, a higher resistance will mean that you have a higher slope for that line. That line will be above the lower resistance line. Another way of thinking about it is if you draw sort of a line of either constant potential difference or constant current, right? So let's do potential difference first. And if I draw this line right here, I can see that for the same delta V, a lower resistance object has a higher current, okay, than the higher resistance object. Equivalently, I can say, all right, to get the same amount of current out, the low resistance circuit will need a lower potential difference than the high resistance circuit, right here. And then if you flip the axes, you find that that trend flips, which is often counterintuitive, so you got to be a little bit careful. The lower resistance material will have a I versus delta V curve or line that is above the higher resistance material if these axes are flipped. And because there is such a nice interpretation of delta V on the vertical axis, you will often see this graph plotted, even though 9 times out of 10, I is the dependent variable and delta V is the independent variable. You should be comfortable sort of going back and forth between these two sets of graphs. In the next video, we will begin to look at sort of what such graphs and such materials might look like for non-ohmic conductors.